Hi everybody, my name is Maxime Chevalier-Boisvert and today I'll be telling you about YJIT, which is a new just-in-time compiler that we're building inside of CRuby. So on the agenda, first I'll tell you a little bit about the project, why we're building YJIT inside of CRuby, some technical details about how it works, and then I'll go over some current performance results. And finally, I'll conclude with a segment about what we can do to improve the performance of just-in-time compilers built inside of CRuby, both YJIT and MJIT. So YJIT, why not JIT? The name stands for YARV-JIT because we compile YARV bytecode. And yeah, you could also say it stands for yet another Ruby JIT because obviously we're far from being the first just-in-time compiler for Ruby. So the primary goal of YJIT is to produce speedups on large-scale real-world software. I work at Shopify, so we're primarily concerned with web workloads, in particular Ruby on Rails. The approach that we've taken, because the CRuby code base is very complex, is to try to build something incrementally. So we started by building a JIT compiler that doesn't support all of the Ruby bytecode, and incrementally we've been adding support for more and more different operations and falling back to the interpreter for anything that we don't currently support. And so far this approach has been working pretty well. The main benefit of the approach that we've taken is that YJIT is highly compatible with all existing Ruby code and packages. You don't need to change your Ruby code at all. It supports all of the latest Ruby tree features, which I think is something that's highly underrated. And it's built at Shopify, but it is fully open source under the same license as Ruby. And we hope to eventually upstream YJIT into CRuby. But in the meantime, we want to find ways to help both YJIT and MJIT achieve better performance. So this project is not just my project, it's a team effort that's being led at Shopify in the Ruby on Rails infrastructure group. But we also had multiple major contributions from GitHub for the last couple of months. So YJIT is very far from being the first just-in-time compiler for Ruby. There's been multiple efforts to build JITs for Ruby. Most of them are no longer maintained, but there's still a few such as MJIT, JRuby, and TruffleRuby that are still ongoing. I'm going to talk a little bit about MJIT and TruffleRuby, which are the most actively maintained. So MJIT has been integrated inside of CRuby for a while now, and it's based on GCC. So basically, it takes all of the source code of the interpreter, and it basically stitches this code together into something that gets compiled by GCC into a module that can be linked at runtime. The main strengths are that it's already in CRuby, it's compatible with the latest Ruby features, it produces good speedups on smaller benchmarks, and it's officially supported on multiple platforms. It has really good portability. Some of the trade-offs with this approach is that it performs best on synthetic benchmarks with large methods, but not always so well on really large programs with lots of tiny methods, such as web-based software. We think that GCC is not really equipped to optimize dynamically typed code. It doesn't really have the right optimizations and analyses. And because GCC is being used as a backend by this compiler, there's limited control over what GCC is doing and over the compilation pipeline. TruffleRuby is an alternative implementation of Ruby based on the Truffle and Graal platform. Its main strengths are it's actively being developed. It has a really powerful optimizer based on partial evaluation. It produces huge speedups over CRuby on many benchmarks. And it has pretty good support for C extensions using an emulation mechanism. Some of the trade-offs are that the warm-up time can be very long, sometimes up to multiple minutes. The memory usage is greatly increased compared to CRuby. And because it's a reimplementation of Ruby, it's not exactly a drop-in replacement. It doesn't have 100% compatibility. And so this brings us to the reason why we chose to build YJIT inside of CRuby. It's because language compatibility is very critical for most real-world users. And this is not a problem that's specific to TruffleRuby. I would say most programming languages that have alternate implementations face similar problems. So JRuby is working towards reaching support for Ruby 2.6. Truffle Ruby is reaching Ruby 2.7 compatibility, but in the realm of other programming languages such as Lua, we have YJIT, which is a really impressive just-in-time compiler that's well loved by the community, but it's falling behind, unfortunately, when it comes to supporting the latest Lua feature, and that's limiting adoption. And it's kind of the same problem for PyPy. PyPy, again, really impressive work, but currently they're working on supporting Python 3.6, whereas CPython is at version 3.9. So by building YJIT inside of CRuby, it's really easy for us to stay up to date with the latest change and support the latest language features. So now for the next section, I'll tell you a little bit about how YJIT optimizes Ruby code. So Ruby is a language that's notoriously difficult to optimize. Just this blog post that was published all the way back in 2012, which I think is really relevant and goes over some of the many challenges. Among other things, every operation on every basic type can be redefined. Methods can be redefined. Constants are not actually constants. Callee functions can write into the local variables of their callers. The method call logic is very complex. And real-world code has lots of small methods, which makes it hard to apply compiler optimizations to method bodies without doing a lot of inlining. But Ruby is also a language in which it's difficult to do inlining correctly. And then there's the C extensions API, which is its own can of worms when it comes to compiler optimizations. So the approach that we've taken for YJIT is to build a compiler based on basic block versioning. This is based on some research work that I started during my PhD building a just-in-time compiler for JavaScript. My work was focused on optimizing dynamic languages and eliminating dynamic type checks. So basic block versioning is a technique that allows us to do type specialization of machine code without doing expensive type analyses by leveraging the fact that inside of a JIT compiler, we can observe the program while it's running. So it's trying to be kind of a reimagination of what a JIT compiler could be. Most traditional just-in-time compilers are method-based, meaning they compile entire methods at once. But basic block versioning works at a lower level granularity where we can compile individual basic blocks as a unit. So we can compile just part of a method. And there's a small but diverse body of literature about the technique. I published 2 papers during my PhD, and there's also been papers on adapting this technique to functional programming languages like Scheme, and also for use with gradual typing. There's 2 key components to lazy basic block versioning. The first is the versioning of basic blocks. So we accumulate and propagate type information, and we specialize different versions of basic blocks depending on context. And we do this by doing selective tail duplication and unfolding the control flow graph. The second is lazy code generation. So we're basically doing lazy tail duplication, and it's kind of like lazy evaluation for code, where the control flow graph is viewed as an infinite data structure that's unfolded by generating code only when needed, only when it's just about to be executed, truly just in time. So how does this work? Well, let's look at a small example. Suppose that we have an if statement like this, where we're checking if some value n is a fixed num. If so, we go to block B, otherwise we go to block C, and afterwards we go to block D. In terms of control flow graph, this looks something like this, where we have the type test is fixed num at the top, and on a true branch we have the block B, on a false branch the block C, and afterwards we merge in block D. So if we take the true branch, when we're inside of block B, we know that n is a fixed num, and when we take the false branch inside of block C, we know that n is not a fixed num. But unfortunately, after we merge in block D, we know that n is either a fixed num or not a fixed num, which means that we know nothing at all. With basic block versioning, we can basically split block D into 2 different versions, D prime and D prime prime. And in D prime, we preserve the type information that n is a fixed num, and in D prime prime, we know that n is not a fixed num. So this is pretty clever, right? Well, what about huge control flow graphs that look more like this? If we have a ton of if statements that are nested Obviously, we can't duplicate everything to preserve the types of every variable everywhere. So how do we work around this? This is where laziness comes in. If we know the default branch is never taken, with lazy basic block versioning, we don't need to generate that code. And so we're not increasing the size of the machine code that we generate. In YJIT, we use lazy block versioning to implement some pretty cool tricks. So it turns out, in a JIT compiler, we often want to specialize code based on the values that we see at runtime. Traditional method-based JITs do this by first doing a profiling pass and then generating highly optimized code. In YJIT, we use a technique that we borrowed from Psycho and its onLift operator, and we call this Deferred Compilation and type capture. So what we do is that for some of the bytecode operations that we want to compile in Ruby, we defer compilation as late as possible using a stub. So we're essentially pausing compilation until we can see the values that occur at runtime, and we generate code only after we've been able to peek at those values. So this technique was first described in this paper by Armin Rigo in 2004. Let's look at a simple example. Here we have a method get that's used to index either into an array or into a hash. So if we disassemble this to get the bytecode instruction sequence, we get a short sequence like this, where first we use the get local to push the value of obj on the stack, get local again to push idx on the stack, then we call opt_aref to do the indexing operation, and then finally leave, which returns back to the caller. So in terms of the code that we generate, first we're going to generate machine code for the two get local operations, and then we're going to install a stub, which is going to allow us to pause compilation until we can actually peek at the values of obj and idx. Now, the first time that this method was called, it was called with an array and an integer. So we're going to install some guards to check that the type that we see at runtime matches what we've seen at compilation time. And then we're going to generate an optimized array get operation. If the code is called with some different types, we're going to install another stub. Then if we call the method again with, say, a hash, we're going to hit that stub, which is going to call back into the compiler and generate more code that's going to be specialized for hashes. So it's going to generate an optimized hash get operation. And then if we ever hit different types at runtime, we're either going to call back into the compiler by hitting a stub, or we're going to fall back to the interpreter for the types that we can't handle. Now for some early performance results. So we've tested YJIT against the CRuby interpreter, MJIT, and TruffleRuby on a variety of benchmarks. The benchmarks that are to the left are synthetic benchmarks, or benchmarks that we've implemented ourselves, and the benchmarks to the right, Cycload, Liquid Render, Active Record, and Railsbench, are all based on real-world software and Ruby packages. The 30K methods and 30K if-else benchmarks are synthetic benchmarks that were created by us to basically force YJIT to generate a large amount of code. So these benchmarks contain several thousand methods that are calling each other into a small loop. And the point here was to look at the effect of code size on performance. We wanted to determine if generating a relatively large code size was going to be a problem for performance. And the answer is a resounding no. It looks like as long as we can compile all of the code, YJIT is able to linearize the code very effectively and is able to get a massive speed up over the interpreter. On the real-world benchmarks, like Cycload, Liquid Render, Active Record, and Railsbench, we see that YJIT is always faster than the interpreter, and it's also faster than MJIT on these four benchmarks. So basically, we have that if we take a CPU and expose it to code generated by YJIT, the CPU is happy. This graph shows basically the warm-up performance on Railsbench for the interpreter, YJIT, MJIT, and TruffleRuby. So what we can see here is that the performance of YJIT and MJIT is relatively stable over time. YJIT is able to generate a speed up very fast on the first iteration of the benchmark. TruffleRuby eventually reached faster peak performance, but it takes over 2 minutes to reach the same performance as YJIT. And later, there's a period where it has a very high latency due to de-optimization and re-optimization. But maybe the most important result of all is how compatible YJIT is. We've recently added tracepoint support, and we're passing all of the CRuby tests with MakeCheck. We're able to match the performance of RubyHead in the Shopify core backend CI. We're matching the performance of RubyHead in the GitHub backend CI. We're again matching RubyHead in Shopify storefront render CI. This is software that renders all the Shopify stores. And we've done some initial tests and found that YJIT is able to run storefront renderer and render Shopify stores in production, and it's able to outperform the CRuby interpreter. So from now, everything is all sunshine and rainbows, right? Well, maybe not quite. There are some performance bottlenecks in CRuby that make it so we can't quite reach as high of a performance level as we would like. And these are things that we can't directly fix just by making YJIT more sophisticated. So people tend to think that just-in-time compilers are some really sophisticated, really advanced technology. And if you just, put a JIT compiler in an existing language implementation, you get a really fast, really sophisticated machine, right? Well, maybe not quite. Actually, what we end up with YJIT is maybe something a little bit more like this. And maybe that's to be expected, right? I mean, after all, maximizing performance requires a design that's generally highly specialized. Race cars aren't just regular cars with more powerful engines. They also have things like more aerodynamic design. They're able to channel airflow to cool engines effectively. They have lighter bodies made of, for example, carbon fiber, racing suspensions, racing tires, high performance brakes, and also special tuning. And of course, engineering always involves trade-offs. In the case of CRuby, we're working with a code base that's over 25 years old, and that's been designed with an interpreter in mind. So what can we do to make CRuby and YJIT faster? Well, to be fast, we think that adding a JIT compiler to CRuby is not enough. Because, again, CRuby was designed with an interpreter in mind, and the design priorities for an interpreter are not always the same as those for a just-in-time compiler. So we think that for maximum performance, some amount of re-engineering is necessary. Here I'm not at all suggesting that we rewrite all of CRuby, but maybe we can target some areas where the JIT compiler needs to interface with CRuby. For example, what are the biggest performance bottlenecks? What are some things that would be easy to improve? And I think by addressing some of these, we can help both the performance of YJIT and MJIT because they're both JIT compilers and they have similar requirements. So what are some of the biggest bottlenecks in CRuby as of now? Well, Ruby is an object-oriented language and it has lots of short methods with many method calls in them. It also has lots of instance variable accesses. So we found that much of the bulk of the machine code we generate is in method calls, so the send and leave instructions, and also instance variable accesses. And currently both of these require many steps, but it's not something a JIT compiler can easily remove because, for example, the format of objects and stack frames are defined by the interpreter, not by the JIT compiler. So now let's look at the way instance variable reads are implemented in YJIT as of now. So the way objects are implemented in CRuby right now is that objects are instances of the RObject struct. And in there, first, there's a bit field called flags that stores various flags about the object. There's a pointer to the object's class. And if the object is small, up to 3 instance variable slots can be stored on the object itself. If the object has more than 3 instance variables, then instead there's a pointer to an external instance variable table that's stored in the object. And this external ivar table can store as many ivars as possible. The size of the external ivar table is also stored on the object. So unfortunately, it turns out that this is pretty inefficient because, as you can imagine, almost all Ruby objects have more than 3 instance variables. And so almost all ivar reads and writes in CRuby need 2 levels of pointer indirection, which is bad for the CPU cache. We think that this could be fixed by some work that we're doing on variable width allocation. Also, unfortunately, Ruby classes don't have all the information that we need. If you want to know if an if an ivar is stored on an external ivar table, you need to check a flag in the object's header every time that you access the ivar. And if we need to check if an object is frozen or not, we need to check the flags every time that we write to the ivar. We think that this could be fixed by using object shapes. Also, it turns out that you need 2 comparisons to check if something is a heap object or not, which is necessary because of Ruby's tagging scheme. And this check happens all the time, everywhere in the code that we generate. But again, we think that this is very fixable. We have the technology and we can make CRuby better. So there's some work that's ongoing with variable width allocation at Shopify, which we think could help us make object representations more efficient. Another key piece of technology is that of object shapes. This is an idea that dates back to Smalltalk, which was one of the languages that originally inspired Ruby. I'm not going to go into details in this talk because my colleague Chris Seaton gave a talk about it earlier today. But the key idea is that each object has a shape pointer instead of a class pointer, and shapes are metadata that tells everything we need to know in order to access an ivar efficiently. This is tested and proven technology that's used in Chrome's V8, Firefox's SpiderMonkey, WebKit's JavaScript Core, and Ruby, and there's no reason why it couldn't work for CRuby as well. So, using object shapes and variable width allocation, we think that we could, for most property accesses, not need to have an external ivar table, and instead have a more flat object representation, which is better for the instruction cache and more efficient in terms of machine code that we can generate. So let's look at a simple example and the code that YJIT generates. So here we have a class foo with a method getV3 that reads the instance variable v3. And then we're calling that method, and finally calling YJIT.disasm to see the machine code that YJIT generates. So the first thing to note is that this is a lot of machine code with a lot of different instructions. If you can't understand what's going on, that's normal. So let's go over it together. The first and last instructions here are just reading the value of self and putting it into a register. And at the end, we're pushing the value on the stack. And then what we have to do inside of getInstance variable, the first thing is we check that the value of self is a heap object. Then we check that this has the class that we expect. Finally, here we know that the ivar is going to be an extended table, so we need to include a guard for that as well. And then at the end here, we're checking if the instance variable is q and def, because if that's the case, then we need to be pushing qnil instead. So how can we make this more efficient? Well, right now we need 2 comparison instructions, a test and a comparison, in order to guard that self is a heap object. But we think that maybe the type tagging scheme in CRuby could be changed so that only 1 comparison is needed. When it comes for guarding for a known class, if we used shapes instead and we could identify shapes by 32-bit integers, we could eliminate a move instruction here and directly have a comparison with 32-bit immediate, which eliminates 1 instruction. Again here, for guarding that the instance variable is on an extended table, if we use variable width allocation and object shapes, we could eliminate this completely. And finally here, for the check for q and def, by using object shapes, we could eliminate this as well, because we know directly from the shape if the instance variable is q and def or not. And finally, by using register allocation in YJIT, it might be possible to eliminate both of these moves. And using type propagation, some of the time we're actually able to eliminate this check as well. So by using a combination of improvements in YJIT and improvements in CRuby, such as object shapes and variable width allocation, we could go from many instructions to just 3 machine instructions to implement getInstance variable. In terms of future plans, here's 2 things that we're currently working on. The first is a more sophisticated backend for YJIT. Right now, the type specialization and code generation logic in YJIT are tightly coupled together, but we think that by decoupling those, we could implement simple optimizations like register allocation and basic instruction selection. And eventually, we also like to have support for ARM64 CPUs, which are slowly making their way into laptops and the server space. Because right now, we only support code generation for x86-64. We'd also like to bring support for object shapes to CRuby. because currently the object model in CRuby is very complex and we think not ideal for JITs, and we think that object shapes could be both simpler and more efficient. We'd also like to collaborate with the Ruby core developers. Some things that we'd like to communicate is that just-in-time compilers, being more complex than interpreters, are harder to refactor, and so stability is good for us and for performance. Some things that we think could hurt us and also could hurt MJIT are major changes to the Ruby bytecode, adding complexity in special cases, and changing the semantics of method calls or instance variable lookups, for example. But we also think that YJIT and MJIT have similar needs. Our plan is to upstream object shapes separately from YJIT, and we think we could also design things like a faster calling convention together, so that basically these improvements could benefit both YJIT and MJIT, and those benefits could come sooner than upstreaming YJIT. And of course, we're also very happy to discuss other improvements to CRuby with the Ruby core developers. So in conclusion, we're still relatively early in the YJIT project. It's been in development for about a year. Our results are still modest, but we think already interesting. And we have a clear path for much bigger speedups. We're building this new JIT inside of CRuby because we think that has a huge compatibility advantage. YJIT is already basically like a drop-in replacement for existing Ruby binaries, and we're already passing all of the CRuby tests. Lazy busy block versioning is basically lazy evaluation for code. It's a way to capture type information as late as possible, and it has a precision advantage over traditional type analyses. If you'd like to learn more about the technology behind YJIT, I've published 2 papers about lazy busy block versioning at eCoop 2015 and 2016, and the information is on this slide. If you'd like to reach out and talk about compilers and about the workings of YJIT, you can ping me at my Shopify email address or at Love to Code on Twitter. And finally, YJIT is available on GitHub at Shopify/YJIT. Yeah, that's all for me. Thanks, everybody.